Good evening, everyone. Let's wait for 3 to 4 minutes and after that we will start. Hello, Mr. Gupta. Hitesh?
Yes, hi, hi.
Yeah, hi.
Yeah. Good
How are
evening.
you? Good evening. So everything is fine? My video, PPT and audio?
Yeah, we can
Yes,
see
yes,
you.
fine, fine.
Okay, thank you. So let's wait for 2-3 minutes and after that we will start.
Okay.
So hello everyone. I welcome you all to this live session number 11 for the course Hydrogen Energy, Production, Storage and Transportation Safety. So currently we are in week 11. So the course instructor is Professor Pratibha Sharma from IIT Bombay and I am this course T. Amit Kumar Sharma. So as you all aware that every week we have a live session. So in this we have discussion about the previous week's course content, like you can say a short review of the previous week classes, and we have discussion on previous year's assignment question so that you can know how to solve the question, what type of question can come in your exam and assignments. So let's start with today's class. So this is the course outline. As of now, we have covered hydrogen production, status, storage we have covered, transportation we have covered, something about refueling stations also we have covered. Now we are in sensing and safety. Okay, so let's see more about this topic. So we will start from questions and then we will go into discussions. Question number 1 is amperometric sensors uses which technique to sense hydrogen? Potential difference, heat generated measured using Q equals to I square RT, diffusion limited current measured at constant applied voltage, resistivity. Think about it. So very basic thing, what is a sensor? So what is this question about actually?
Amperometric means it's measured, I think, ampere. So maybe the voltage is remain constant. So like that diffusion limited current measure at constant apply voltage, option C.
Okay, we have an answer, option C. Okay, let's see. So yes, your answer is correct. Correct answer is option C. So in amperometric sensor, the technique that is used is the diffusion limited current measured at constant applied voltage. Okay, so hydrogen sensors. Okay, so the hydrogen sensors are very important because we know hydrogen is colorless, odorless. Okay, so it's very difficult to detect. And also, if you go through the flammability limit, so for hydrogen, it has very wide range of flammability limit. Anybody remember the limit? The lower limit and upper limit? So
Yeah.
it's
So lower limit is 4%.
okay. And upper limit is
Not sure. Might be
70%.
100%.
yeah, almost 75%. So this is the range of flammability for hydrogen. So as low as like 4% of concentration and as high as 75% concentration considered as the flammability limit for hydrogen. Okay. Now let's go through more about the sensors. So due to this high flammability range, colorless, odorless nature, and it's very light, okay, very small element, so it's very easy to leak also from minute gaps. So due to this, we should have very good sensors that can sense the hydrogen. So for safety purpose, we need to have very good hydrogen sensors. So this amperometric sensor comes under the electrochemical sensors. Okay. So in this, it's two type, amperometric and potentiometric. So in amperometric, we have covered diffusion limited current at constant applied voltage, and potentiometric, potential difference or EMF. Based on this, we calculate the percentage of hydrogen. Okay. So in this, we have a sensing electrode, a counter electrode. So here you can see the hydrogen reaction, that is 2H plus 2 electron. Then at counter electrode is oxygen react with the hydrogen ions and form water. So the flow of electrons from anode to cathode, current is proportional to the hydrogen concentration. So basically here we are measuring the electron transfer. Okay, based on, so basically the current from the, if you know the current, and that is happening due to the hydrogen only. So with this equation you can find, you can have a calibration and you can measure the concentration of hydrogen. So the benefit is that it has a wide operating temperature range, -20 to 80 degree, or even higher temperature with ceramic electrolytes, and wide range of detection. So you can detect 5 ppm in argon to 100%. So it's a good detection range. Long life response time, low humidity levels, low interference from other gases. So if there are other gases are also present, then it don't have that much of interference. So this is about the electrochemical sensors. For more detail, you can refer to the class notes or a reference book. So first, requirements for hydrogen sensor. So hydrogen is involved in various process industries. Okay, like in for the sense of ammonia and methanol, hydration of hydrocarbon, desulfurization of petroleum products, production of rocket fuels, metallurgical process, nuclear reactor safety, coal mines, transformers, semiconductor industry, lightning, hydrogen used as coolant in turbine generator, fuel for space application, production, storage, transport, and utilization. So these are the areas where we need hydrogen sensors. And nowadays, we all are witnessing the change in energy transition. Okay. So now every country is moving from fossil fuels to green fuel, and hydrogen is playing a major role in the green transition. So every country is coming up with numerous hydrogen projects. Okay. So basically, the thing is that we want to replace the consumption of fossil fuel or to reduce it up to a large extent so that we can limit the global warming and climate change. So nowadays the requirement of hydrogen sensor is much more on small scale basis also, because nowadays various industries, small startups, they are coming up with new hydrogen technologies, hydrogen production technologies. They are coming up with the storage and transportation technology development and all. So now the requirement of, you can say, in this sector is increasing, and also like actually some small R&D units are also there, so they are developing number of projects. So we need to identify low cost sensors also. That's also a challenge. Okay, because for these applications, they are mostly happening in the industries on large scale, so that they can afford any sensor that can have very excellent range, okay, stability and all. But for new startups, new companies, small scale companies, we need to have a sensor that can have good accuracy with low cost. That's a challenge. Okay, so these are the areas where we need the hydrogen sensors. Now the requirement of hydrogen sensor. So the requirement is it should detect low to moderate level 0.01 to 10%, because we know that the flammability limit start with 4%. So it should detect very low percentage of hydrogen. There should be high accuracy and precision, because we know hydrogen highly flammable, so that if the accuracy is not good and there is a leakage, so there can be an accident. So the accuracy and precision should be very good. Interference with other gases and humidity should be minimum, and the sensitivity should be very good regarding this, because when we are having like a mixture of gases, like you can say syngas, or also like there are other gases also there, you are having some kind of reforming reactions, so there will be hydrogen, CO2, CO. Okay. Me- so in that case also, so there should be minimum interference due to other gases, otherwise your reading will be not correct. Okay. It should work well even in unfavorable operating conditions. So the operating condition should be having a wide range so that it can also work in unfavorable operating conditions. Stable output with low overall noise. Response and recovery time should be less. It should be like you can say small, compact, robust, long life, low power consumption, simple to operate and maintain, and cost effective. So the important. So these are the basic requirement from a hydrogen sensor. Now, if you want to have a sensor, so there are different techniques, different, you can say, systems to detect the hydrogen. So different methods are there. So we can detect hydrogen via mechanical, triboelectric, electrochemical, thermal, resistive, acoustic, work function based, optical, catalytic. So there are different routes to detect the hydrogen. Each route have their own you can say method or mechanism, and they have their own pros and cons. So we need to decide the correct sensor according to our process and the limitation that we have in the our process. Now we will go through one by one. So in thermal sensor, basically in these types of sensor, we use a thermal conductivity principle to detect the hydrogen. So thermal conductivity of hydrogen is like you can say 0.174 watt per meter Kelvin 20 degree against air 0.026 watt per meter Kelvin. So heat loss from a body to surrounding environment, and wide detection range this type of sensor can detect less than 1 to even 100% H2. So it's difficult at lower ranges, so it can be used with another sensor. So for lower ranges, it's not good, but for you can say less than 1, but not in this range, up to 100% it is good. Long life, no poisoning, low response time. Any change in the ambient temperature need to be considered. So because it's working with the thermal conductivity, so it's at like you can say it's calibrated at a fixed temperature, ambient temperature. If there is change in your ambient temp conditions, then you need to recalibrate this. Okay, so you have to consider the ambient conditions also. Many interfere with the gases of similar thermal conductivity. So if you are having a composition which are having the similar thermal conductivity of near you can say hydrogen, then there will be interference. Okay, so you can say it's kind of a Wheatstone bridge. There's a test electrode, uh, test resistance. You can say or there's a reference resistance. So based on thermal conductivity change, suppose if there is air, then there will be no change. If there is hydrogen and then air, then there will be some difference, and you will receive some signal into this, and that signal will be translated into the hydrogen concentration. So electrochemical, we have just covered this slide. So in potentiometric, measure potential difference or EMF operated zero current. So electrode potential is related to the hydrogen gas concentration. So this is the Nernst equation. E equals to E naught plus RT upon ZF ln A upon A naught. So this refers to the concentration of hydrogen. It's in logarithmic nature. Difference from amperometric sensor, measure signal independent of sensor size and geometry. So it's important thing. So the signal is independent of sensor size and geometry. So you can also develop a very small sensors out of this. Response varies logarithmic with hydrogen concentration. So you can say it's varying with logarithmic nature. Thus lower accuracy at high concentration. Okay. Amperometric are more widely used. Electrochemical sensors consume low power, operate at low temperature, wide detection range, 10 ppm in nitrogen to 100%. Response time is 10 second to 100 second. Even lower reported in few studies, less than 2 seconds. PD on ITO 0.1% you can go up to go, and SNO2 be best scaffold 40 ppm. Now the electrical conductivity or resistivity based sensor. So these are based on the resistance variation. MOS used responsiveness towards reducing gases. Electrical properties changes. So here we have a substrate, L2O3, SiO2, etc. Then there is an insulating layer, heating element, electrodes. Okay. So PCB used on copper electrode used for gas detection, and flexible substrates with inkjet printing for gas sensing. Resistance across the electrode, difference in resistive load of element is calibrated with the ambient gas concentration. So the resistance across the electrodes and difference in resistive load of element is calibrated with the ambient gas concentration so that you can know the concentration of hydrogen. So some I'm work at high temperature as a heating element. So they are the reaction. Now the work function based sensor. So in this the work function, so hydrogen atoms at interface are polarized, giving rise to the dipole layer. It changes the work function metal, shifting the energy levels at metal insulator interface. The dipole layer correspond to a measurable voltage change delta V added to external voltage. So this device can be used to measure metal oxide semiconductor transistor MOSFET. If it used to change into electrical signal, the metals used in this PT, PD, RU, nickel, etc. So the MOS have better sensitivity than MS, and the oxide layer we use SiO2, WO3, HFO2, and Ga2O3. In mechanical type, so it is based on the physical property of metal. So metal sensitive to hydrogen coated on one side of a micro cantilever. So you can see it's a cantilever. It's a fixed stand. Then there is a micro cantilever. There is a beam. So here we do the PD coating. Okay. If there is hydrogen, then that will come onto this, and this side you can say you can like just consider the weight. It will increase, so it will put some stress here. So it will come a little bit down. So based on that, it's like volume expansion prohibited by substrate, but stress induced are transferred as a mechanical bending or curvature in the cantilever. So complex fabrication procedure, delamination of metal coating can be there. So you can use chromium with palladium, PDNI, PDAG for stronger adhesion, so that there will be no demyelination of metal coating. Uncoated silicon microcantilever only when one type of gas. Detection up to 0.02%. Change in response frequency measured in silicon microcantilevers. The concentration of hydrogen increases, the fluid mass density increases, increase in equivalent mass of cantilever, and decrease the response frequency. So basically, with this frequency, we can calibrate that with the hydrogen concentration. The optical sensors. So we can also optical sensor. They are based on reflectivity measurement, interferometric measurement, measurement of SPR, then evanescent field measurement, chemochromic oxide coating, fiber break grating, optical time domain reflectometry. So for more detail on these, please refer to the class notes or a reference book. The advantage of optical sensors are you can have fast response, sensing without any explosion. Disadvantage, cross sensitivity with other gases and ambient light. If there are other gases also there, then they can interfere the results, and also the ambient light can interfere the results. Then the acoustic sensors. So it changes in the surface properties. Okay, based on that, surface generated acoustic waves to QCM or SAW sensors. So here the PD doped SNO2 coated over LiNBO3 piezoelectric material. So PD doped graphene used in SAW sensor. Velocity of sound velocity of sound in hydrogen gas is 1314 millimeter per second, and in air 346 meter per second. So the sound velocity measurement can be used to detect the hydrogen gas due to this huge difference. Then sound generator used with receiver to detect propagation time in different gas concentration. So advantage, high sensitivity and reliable, low power consumption, wide range of detection, fast response. Disadvantages, sensitive to interfere sound waves and vibration, unable to operate high temperature, long-term stability lacking, and interference from other gases. Now in catalytic sensor, so heat released from the oxidation of combustible gases on surface of catalyst is used to measure the hydrogen concentration. So it's a polyester type. So platinum nanoparticles lodged graphene in aerogel. We can have very fast response. You can say 0.97 second. Slow power consumption and negligible cross sensitivity. We can also have a Seebeck effect type of thermoelectric sensor. So oxidation of gas on surface of catalyst increases temperature and volume changes. So platinum nanoparticle shows high Seebeck effect, high response signal of 0.22 millivolt at 10 ppm and fast response less than 50 millisecond. Wide operating temperature, stability. Disadvantage like high power requirement, interference with other gases, high response time. Now the triboelectric sensor. So it's also have advantage like cell powered devices, fast response, complex design and fabrication. So in summary, we can just quickly go through the advantage, disadvantage of thermal sensor, fast response, low cost, stable, wide measuring range, simple design, robust. Disadvantage sensitive to interfering gases, low detection limit, heating element reacts with the gases, electrochemical, sensitive, low power consumption, working at high temperature is possible using ceramic electrodes. Heating element is not required. Issue is with the cost, low life, cross sensitivity, specific electrolyte required. Mechanical, small size doesn't require oxygen. Can work in explosive environment, micro machining possible. And mechanical issue is the fabrication difficult, cross sensitivity, slow response, and aging effect. Similarly for resistive sensor, high sensitivity, low cost, wide operating temperature, simple and easy design, fabrication, low power consumption, fast response. Disadvantage, humidity, poor sensitivity, requires oxygen affected by gas pressure. Then the work function size, small size, fast response, low power requirement, low cost, less influence of ambient conditions. Disadvantages, hysteresis losses, possibility of drift, saturation occurs at modest concentration. So different methods of sensing based on different working principle we have seen. We have seen that they have different sensitivity, LOD operating parameters, power requirement and complexity. So selection of S2 sensor is application specific. So based on application, based on your range, operating condition, your economics, based on that you need to decide the sensor. So S2 is colorless, odorless, tasteless, flammable gas, cannot be detected with the human sense, have certain properties which makes it essential to detect its presence and quantify its concentration. So the fast and accurate measurement is essential to avoid any potential risk of formation of an explosive mixture within air. Requirement is faster, accurate, highly selective and sensitive method. Sensor should be low cost, compact, small and should have fast response. The improving selectivity, sensitivity, reliability and reducing response time. What is the meant work function? So just we have covered a type of sensor which include the work function. If you have gone through the class videos, then you know the answer
Option
is
A.
yes, nice. Option A. So the work function meant to the minimum energy required to remove electron from metal surface to infinity. Okay, the minimum energy required to remove electron from metal surface to infinity. The uncoated silicon micro cantilever type of mechanical sensor uses which method to measure the concentration of hydrogen? We have just covered. Option A, change in resonance frequency, change in resistance of sensor, change in electrical conductivity, change in potential difference.
It's a option A, change in resonance frequency, mechanical based.
Yes, let's wait for another 1 minute. Anybody else? Is anybody here from mechanical engineering background?
Yes.
Yeah, I'm from mechanical.
So do you want to explain what is a cantilever beam?
Cantilever beam
Cantilever beam is
yeah,
okay.
please,
You
please.
explain. Anybody
Yeah,
else?
cantilever beam is a beam which is supported from one side and free on the other side. On.
Just give me a minute. Yeah. So please raise your hand who want to explain. Then I will call your name. Yeah, please raise your hand. Okay. Okay, Gulab Chand, please let us know what is a cantilever beam.
Yeah, cantilever beam is a supporting beam which is fixed from one side and free on the other side.
Yes, yes, nice. So what kind of like in this sensor, what we are doing actually?
It is measuring the vibration basically, which I could understand, and the resonance of that vibration is measured to check the change in frequency, resonance frequency.
Yes, nice. So and anybody else was there? Who was? I think one more guy was there. Who want to explain about the cantilever? Anybody else? Okay. So cantilever beam one end is fixed. Okay. So you can apply loading here, here, like anywhere. Okay. So based on the point of loading, the deflection or you can say the bending will be different. So this is used in mechanical engineering, but here we are using the same concept. So here you are doing some kind of coating with a material, and if hydrogen gas is there, then that will come here, absorb, and it will increase the mass, and this end will apply some, you can kind of, you can like act as a loading, and there will be some stress, due to that it will bend. Okay, then there will be, you can say, try to bend, or there will be some resonance frequency will be there. So based on that you can measure the concentration. The answer is option A. Thermoelectric sensor are based on which effect? Photoelectric, Seebeck, Hall effect, Doppler effect.
Option B, Seebeck effect.
Okay, okay, Jayaprakash, we have an answer option B. So what is Seebeck effect?
Two dissimilar metals are connected at two joint points. Temperature difference is given. Then due to that, some current is flown between
Yes.
the
Yeah.
metals.
Right. So if you are running to dissimilar metal at different temperature, then due to that there will be some EMF will be produced. Okay, so it is used in the thermocouples to measure the temperature. So the correct answer is option B. So in thermoelectric sensor, they are based on the Seebeck effect. Which method is effective for multi-point sensing of hydrogen using a single device? Option A, interferometric; B, evanescent field measurement; C, optical time domain reflectometry; and fiber Bragg grating. So the correct answer for this is option C, optical time domain reflectometry. So I'm also not aware of this in detail, so please refer to the class notes to read more about this. The nature of electromagnetic field decay in evanescent field measurement exhibits space behavior: parabolic, hyperbolic, linear, exponential. The answer is D, exponential. So the evanescent waves are non-propagating electromagnetic waves with energy concentrated near the source. Okay, so this result in exponential decay with distance from originating surface. So the answer is D, exponential. Hydrogen is not suitable for CI engines because hydrogen density is low, hydrogen causes embrittlement, hydrogen has high autoignition temperature, hydrogen has diffusivity.
C.
Okay, so we have one answer C. Anybody else?
Yeah, option C, auto ignition temperature, because in compression engine it required the temperature to ignite. In hydrogen ignition, auto ignition temperature is more than 500.
Sorry, what?
Actually, hydrogen auto ignition temperature is high, and in compressed engine means C engine we required we have to compress. So we cannot achieve this temperature.
Mm-hmm. Okay, right. So let's start from the basic. What is a CI engine?
CI engine means the compression ignition means here the air will be compressed. In the compressed air, so temperature will rise. Okay, so it's a compressed air with high temperature, and you are injecting the fuel. Okay, so in that temperature, it will be burned. So that is the compression ignition.
Okay, and what is the SI engine?
In SI
Anybody else?
engine,
No, not you, please. Anybody else? What is SI engine?
There is spark in ignition in that, where injector is used and spark plug is used.
Okay, where injector is used in SI
And
engine.
no, a spark plug is used.
Spark plug and where is the injector is used?
Injector is used for in diesel engines.
Yeah, diesel engine. Okay.
Yeah,
Anybody
diesel.
else? So I want to, like, everyone should participate in this discussion. So we have two answer, two responses. Anybody else? If you want to add any point regarding the SI engine and CI engine. Gulab Chand.
Yeah,
Okay.
the points which has been said, it's completely matching to the requirements. It's like a SI engine, spark ignition engine, which is normally a petrol engine, whereas CI engine are the compressed ignition engine, which represents the diesel engine.
Okay, so what are the major differences in both? First, I think one of you already told that okay, in this we are first compressing the air, then injecting the fuel, and in SI engine, what we are doing?
In SI engine, we are injecting the air fuel mixture and then we
Yes,
are compressing it. Then a spark. We give a spark, the energy. Okay.
yes. So basically, in SI engine, we are injecting the air fuel mixture. So first we are having a carburetor, then we are mixing both air and fuel, air and petrol, and then we are putting that into the cylinder and we are compressing that. After when the piston reaches the TDC, then we give a spark, okay, and that will burn the fuel and we will have a power stroke. And in the CI engine, we are only giving the air in the inlet, like in the first stroke. Okay, then the air will be compressed. Then we have injector. Through that, we will introduce the diesel. Okay, so this is a major difference. Now, anybody just tell me what is the general compression ratio we use in diesel and in the CI and SI engine?
Diesel, I think it is 14 to 18. So
Okay.
ideal is 16.
Mm-hmm.
Uh, SI, I'm not sure it is lesser than the diesel because it needs spark, so we can have lesser compression.
Yeah.
I think it will be in the range of 8.
Yeah.
Okay.
10. Yeah. 8 to 12 or 9 to 12. Okay. For the CI, 14 to 18. Okay. So basically, the compression ratio will be higher for the CI engine so that the temperature should be enough for the burning of the fuel. Okay. So basically, this is a difference in both engines, and the difference is due to the properties of the fuel. Okay. So if you compare the basic property of diesel and petrol, then there's a huge differences. Based on that only, there are differences in the engines also. Okay, now similarly we are having hydrogen also. So due to that also we will have some changes. Now let's come to the question. So hydrogen is not suitable for CI engine because, now come to the question, why it is not suitable for CI engine and we can use this for hydrogen in for SI engine. Why? So
Uh, yes, actually hydrogen have higher auto ignition temperature. In the CI engine, we don't put the spark, so there is no spark or energy there. So it is to be reached to the higher auto ignition temperature.
so but
So
uh, okay, so as you are saying that we don't give the spark in the CI engine. So, but I can increase the compression ratio. Then if I
yes,
increase the
in
compression, the
case
temperature
of
will increase. Yeah.
we can increase the in compression ratio by say 30 or more. And what will happen? So engine will be heavy, a huge engine will be like the cylinder thickness and everything will increase. Okay,
Yes, yes.
so
Because if you are
vibration.
increasing the compression ratio, then basically the you are increasing the compression ratio, the pressure will be very high. Okay, for that region, and due to handle that, your requirement of cylinder material, your enclosure and everything you need to change. Okay, and that will require a huge cost, and also the size and everything will be vary. So due to that, and also the for the other component, the pressure ratio is limited. So in that limited pressure ratio, we cannot achieve the temperature that is sufficient for the hydrogen burning. Due to that, hydrogen is not suitable for CI engines. So the correct option is hydrogen has high auto ignition temperature. Now what is that temperature? Anybody? roughly about?
I think 500.
Yes. So the autoignition temperature of hydrogen is near 500 degrees centigrade. So in spark engine, you can say we have already, the spark is there, so that can be used to ignite the hydrogen gas. So the correct answer for this is option C. So the first fuel was hydrogen plus oxygen used in IC engine. It was patented by the derivatives way back in 1907. So no carbon and hence no carbon emission, CO or soot. So you can say it's only hydrogen and oxygen. High flammability limits. We know that the limit is what is the range? 4% to 75%. So air fuel ratio 34 to 1 or to 180 ratio 1 by mass. Then it support low lean combustion, help in low NOx emission at low lean combustion, and helps in cold start. So high flammability limit also have some advantages. Okay, high autoignition temperature 500 degree against 245 to 280 degree for petrol and 210 degree for diesel. So can work safely at high compression ratio. The benefit of hydrogen in IC engine can achieve higher thermal efficiency. Low density. So if you compare the density, then 10.1 megajoule per liter against 34.6 megajoule per liter in petrol. So its stoichiometry occupies 30% of volume against 1 to 2% in petroleum fuel, less mixed calorific value, and 85% of power output compared to petrol at stoichiometry. So if you compare like this is cylinder volume, and if you're using the gasoline, so that will occupy only this area, and the whole will be for air. But if you for the same power output, if you have the hydrogen, so it will use 30% more volume. So you can see the area occupied with this. So that's why we can use liquid hydrogen premixed or high gases, high pressure gases hydrogen. Okay. High flame velocity, 10 times higher than petrol. So flame velocity is very high. So it can run at higher RPM and higher compression ratio. Then due to high flame velocity, the chances of knocking is higher. Lean mixture mitigates the issue. If you use lean mixture, you can mitigate this issue. What is knocking?
I think it is related to vibration.
Yes.
Knocking.
So basically, please mute yourself. One of you is there is echo. Okay. So suppose this is your cylinder, okay, and here you have your spark plug. So suppose these are you can consider like once your spark is giving heat to this front, then it will ignite and it will transfer the heat to other, and they will each you can consider like each line as a fuel front, okay. So your flame front will start traveling like this. So it should travel in line, okay, as like smoothly. But what happens sometime due to change in the some parameters, this end front will ignite before this propagation, like the spark is coming down here, will reach here, but suppose it at this distance only, and this will ignite. And what will happen? The uniformity in this combustion will not be there, and sudden combustion will be there, okay, of this front. And due to that, this will also, and maybe the next front also. So you can say this front will ignite before time, okay. So due to this, you will hear abrupt sound, that is called knocking. So in the hydrogen, the flame velocity is very high. So flame velocity is very high actually, okay, and the temperature also, so that sometime the end fronts will ignite very quickly, so the knocking will be there. So if you use a lean mixture, so you can mitigate this issue. High diffusivity, so ensure good pre-mixing, advantage in port injection, direct injection, low quenching distance, 0.6 mm against 2 mm for petrol, so less wastage of fuel. So if we compare the NOx emissions, because hydrogen, if we are using as a fuel, then there will be no carbon monoxide or hydrocarbons, but only will be NOx. Okay. So you can see if we are using the lean mixture, so you can see we can also limit the NOx emission. So at this point, you can see the NOx emission is very low. But if we are going at 0.6, but here we cannot go in this range for the petrol, for the gasoline engine. So we cannot limit the NOx emissions and also hydrocarbon CO emissions. In which fuel-based engine the knocking is higher? Diesel powered, hydrogen powered, dual fuel, diesel powered engine.
It is, it will be hydrogen powered.
Okay, why? We just discussed.
That flame high flammability.
Yes. Yeah, high flammability is there, and also the flame velocity.
Flame.
Just we covered, no? The flame velocity is 10 times higher than petrol. So due to this, the last front will ignite very quickly. Okay. So basically, your fuel will ignite before your full, like this. There we are having timings, stroke timings for the combustion and all everything, so that it will, the full fuel will ignite and you will hear a sound called knocking. So the hydrogen powered engine, due to the flammability and high flame velocity. Which form of energy conversion takes place in the fuel cell? Electrical to chemical, chemical to electrical, chemical to mechanical, and heat to electrical.
Chemical to electrical. B.
Chemical to electrical. So what is a fuel cell?
In the fuel cell, we inject the hydrogen, so the electrons are generated. It's like a reverse of electrolyzer.
Okay.
In fuel cell, the H2 gas, hydrogen and oxygen is being feeding, okay, as reactant, and inside hydrogen, oxygen, that rebonding happen, and in turns electron produce. That electron is being separated and it's being collected uh, from one side. So directly we are getting this from the chemical reaction, we are getting that electricity.
Okay, so in simple words, we can say the fuel cell is an electrochemical device that converts the chemical energy into electrical energy by means of electrochemical reactions. So chemical to electrical. So brief history about fuel cell. So demonstration of gas voltaic battery by William Robert Groove in 1839. So he proved that an electrochemical reaction between oxygen and hydrogen gas produce electricity. Then the Ludwig Monde and Charles Langer introduced the term fuel cell. So they used coal as a fuel and obtained 20 ampere per meter square at 0.73 volt. Then the Langer and Monde cell was modified to make the first alkaline fuel cell. In 1950s, NASA started developing fuel cell for space mission. So fuel cell is not a new technology, it's very old technology, but due to like in between the very low fossil fuel prices and all, it didn't went off. But nowadays, due to rising concern of global warming and all, the pace of R&D and commercialization and technology advancement of fuel cell is increasing very rapidly. Since 1970, there has been an interest in using fuel cell for vehicular application. So basically, you can consider a box, a black box like this. Here you will insert the hydrogen and oxygen, and it will produce the electricity and water. So inside there will be anode, electrolyte, cathode, and other things. But this is the like input and output. So based on different electrolyte, anode, and all the different fuel cells, we will go into detail. So we are converting basically chemical energy into electrical energy. So input you can see we have hydrogen and oxygen. So HS bond, OO bond, and we are forming water. So these bond will break and new bond will be formed. Okay. So in this there will be some energy release will be there, and we are having a connection. So the electron will be transferred from the outer circuit and we can get the electricity. So it's an electrochemical device in which the chemical energy is directly converted into electrical energy. So fuel plus oxidant, electrical power, waste heat, and water. So these are the reaction. H2 will oxidize, you can say 2H plus 2 electron. Then the oxygen 2H plus half oxygen plus 2 electron convert into H2O. So it's the reaction for H2O2 fuel cell. So what are the advantages of fuel cell? So it's more efficient than combustion engine as there is direct conversion of chemical to electrical energy. Okay, now what is the limitation for combustion engine? How we limit the efficiency of a combustion engine? How the efficiency is limited? By which term we limit the efficiency of combustion engine?
So
Unburned
it's many,
fuel.
yeah, it's many temperature also a limitation. If you increase the
Temperature,
temperature,
okay. Yeah,
yeah,
those are
so
the parameters that can affect the efficiency. But for any combustion engine, the maximum efficiency that you can get, what will be that efficiency?
40%.
No, 40%. I'm talking about a theoretical efficiency that you can achieve through a combustion engine. If you have gone through the like principle
Uh,
of combustion engine, Otto cycle, diesel cycle, dual
yes,
cycle.
Is it not Carnot efficiency? I mean,
Yes, correct.
so
So the
that is
Carnot efficiency, yeah.
so
So the
Carnot efficiency is 40%, I think 40% or 42%.
Carnot efficiency, if you can only calculate if you have given the temperatures, na. So if you have given the temperatures and you can consider a data based on that, you can calculate the Carnot efficiency. So the thing is that as we have not given any data, so the Carnot efficiency is the limiting efficiency for a combustion engine. And how the combustion engines are working, how they are converting the energy.
From chemical energy, then heat energy to mechanical energy.
Okay,
Uh,
so
yeah.
if I consider the route, then in combustion engine also we are using a fuel that have chemical energy. So the route for the combustion engine is chemical energy. Then what will happen?
Heat energy,
Yes, it will be converted into heat. Then this heat energy will be converted into
mechanical energy.
mechanical work. And this mechanical work you can directly rotate a shaft, or you can you can use directly in the for the vehicle application, or you can also rotate a dynamo
Uh,
and generate electricity.
yes.
Okay, then electricity. And in fuel cell, what happens? The chemical energy to electrical energy. So see, we are eliminating two steps using fuel cell as compared to the engines. And in combustion engine, because we are generating the heat, and heat, what is heat? Heat is a low grade or high grade energy?
Uh, it is high grade of energy.
No, heat is a low grade energy. Work is considered as a high grade energy, and we are considering low grade to high grade. So heat is a low grade energy, we are considering low grade to high grade. So we can only convert a portion of heat into the useful, or you can say in mechanical work. Okay, so there will be loss of huge portion of this low grade energy. Okay, and this is limited by the Carnot efficiency. But in the fuel cell, there is no such limitation because we are directly converting the chemical energy to electrical, and we are not having the combustion. Okay, the thing is that if you are having the combustion and you are producing the heat, then there will in the combustion there will be so much of entropy generation will be there, irreversibilities will be there. Okay, and you cannot reduce those irreversibilities, and that will reduce the net energy output. So basically in fuel cell, we are directly converting chemical to electrical. And the other benefit is that independent scaling between power and capacity. So if you compare the combustion engine, then if you increase the size of the engine, then the efficiency improves. But this is not the case with the fuel cell. Fuel cell, the efficiency is independent of the size or capacity. Okay. So if you are having a fuel cell of 500 watt or 500 kilowatt or 5 megawatt, the efficiency will not change because efficiency is not depending on the size or capacity. It can be easily scaled up. So the scalability is very easy, reliable and long lasting as there are no moving parts, silent operation. Okay, as compared to the engine, in engine we are having so many moving parts. Okay, but in the fuel cell, it's totally electrochemical. So there are no moving parts, long lasting and silent operation. No undesirable products and particulate emissions. So we have seen that we are not doing the combustion. Okay. So the emissions will be, no emission will be there if you are using pure hydrogen. Okay, some fuel cell you can also use hydrocarbon fuel. In those fuel cell, there will be some you can say CO2 and all will be there, but normal hydrogen fuel cell, there will be no particulate emissions. But we also have some disadvantages. High cost, that's the main factor. The cost of fuel cell is very high due to the costly material that are used as anode, electrolyte, and cathode. Okay.
But one thing in fuel cell is generating that heat, and that heat will be waste. I mean, so that also we can say in terms of its emission. Though it is not directly with the carbon dioxide, but there will be heat generation.
No,
Okay,
heat
and
generate.
in some case the NOx also. Though NOx we can control here, control here, but heat generation will be always there. How we will harness that heat? Heat.
Yeah, heat generation is there, but that is not as a emission actually. So emission refer to the that is considered as a, you can say the that harming the environment actually, na emissions. So the heat
Uh,
is there. Okay, so either you can recover the heat or you cannot recover. It depend. Okay, so basically heat release will be there so that that heat will you can increase because you are having one side the oxygen. Okay, so for the fuel cell you can maintain the temperature by increasing the flow of air, okay, or oxygen. So your oxygen stream, your outlet stream, that will be heated. So either you can put some heat exchangers on the downstream side from where you are getting your anode and cathode outlets, you can recover heat, no issue with that. Because if you go through the high temperature fuel cell, solid oxide fuel cell, so those fuel cell, your off gases are at very high temperature, around 9 more than 900 degrees centigrade. Okay, and the whole system is based on the heat integration only, because your at inlet you require around 750 800 degrees centigrade. Your fuel cell is operating at 850 degree, 900 degree. Okay, so how will you maintain the temperature? So you cannot provide heat like energy continuously to maintain that. So what will you do? So you use the exhaust heat. Okay, so there will be reforming reaction and the exhaust heat will be very high. So you will put some heat exchanger, you will do some investment, you will use your heat exchanger to preheat the inlet stream. So basically, suppose your inlet fuel and air is at 25 degrees centigrade. So you will use the exhaust stream that is at 900 degrees centigrade to preheat your inlet stream to a certain temperature. So sometime you can go up to like 700 or 750, so that you will have to give a very few heat, like a small amount. You have to give very small amount of heat for your inlet streams to maintain the inlet temperature to the fuel cell. So the heat integration is very necessary, but in low temperature fuel cell, it is not uh, an issue, but the heat generated will not that much. So it depend on the fuel cell to fuel cell. But yes, you can harness the heat generated by placing some heat exchangers. Okay. Yeah. So disadvantage like fuel availability and storage issues, alternate fuels, poisoning and start stop cycling. These are the disadvantages with the fuel cells. Now, what is the principle of operation of a fuel cell? So current produced depend on the size of reaction area or interfacial area. Okay. The reactant delivery to the fuel cell. So continuous efficient delivery of reactant required. Flow field plates having channels transport gases. So basically suppose this is your electrolyte, then you have anode, then you have cathode. Okay, so this is, you can say, fuel. From here oxidant, and you have connected with, you are collecting the electrons. Okay, so basically there should be continuous efficient delivery of reactants required, flow filled plates, saving channels, transport gases. So this is your area, so you have to uniformly disperse your fuel over this area so that you can have reaction all over the surface. Okay, so we are using different channels so that uniform distribution of the fuel over the anode surface should be there. Now electrochemical reaction, so the current generation directly related to the speed of electrochemical reaction. High current output is desired, so catalysts are used. So we are also using the catalysts. Ion conduction through the electrolyte and electron conduction through the external circuit. So the ions will be conducted through the electrolyte and electrons through the external circuit. Ion transport is less efficient and contributes to resistance losses. Thin electrolyte should be used for ion transport. So if you increase the thickness of your electrolyte, so that will increase the resistance to the ions, and that will decrease the net reaction efficiency. And so basically the produced current will decrease. So we want to have thin electrolyte so that there will be very low or very less losses in the ion transport. The product removal from fuel cell important as otherwise prevents new fuel and oxidant reaction. Water flooding may be issue in fuel cell. So removal of the, because at one side the water will be formed, so you have some proper mechanism to remove that product. Otherwise that will hamper the reactions. Water flooding may be an issue in many fuel cell. So now relation between Gibbs free energy and voltage. So electrical work done by charge equals to potential difference multiplied with charge. So W equals to E is potential difference, Q is the charge, and we know the charge is N multiplied by F, where N denotes the moles of electron transferred and F is the Faraday's constant. So you can say W equals to N E F. Okay. So the maximum electrical work is the negative of Gibbs free energy for constant pressure and temperature. So W is minus delta G. So the Gibbs free energy is minus NFE. Okay, put the value of W. So in hydrogen oxygen fuel cell, there's a basic reaction H2 plus half O2. H2O is full cell reaction. Half cell reaction we have seen earlier. So for liquid water as product, if you're having liquid water as product, then delta G will be minus 237 kilojoule per mole. And standard state reversible voltage by this fuel cell will be, you can calculate from here, E equals to minus delta G upon NF. So minus delta G upon NF, it will come to 1.23 volt. Now thermal efficiency will be useful energy upon delta H. So the useful energy, you can consider that delta G is the useful energy 237.1 and delta H 285.8 for water, enthalpy of formation. So efficiency is 0.83. 83% is the ideal efficiency. Thermal efficiency, useful power upon delta G by 0.83. So 0.83 multiplied by V actual upon V idle, and ideal fuel cell voltage at 1 atmosphere 25 degrees 1.229 or 1.23 volt. So if you put the value of this, so it will come, the efficiency will be 0.675 multiplied by V actual. Now net cell efficiency will be voltage efficiency and fuel utilization factor. So this factor is that normally if you are having the full hydrogen supply, then you are not using the whole hydrogen. Maybe you are using 85% of that only. So the remaining 15% will come from the anode exhaust or your electrode exhaust. Now we are having different types of fuel cells. Okay, the proton exchange membrane, molten carbonate, alkaline, phosphoric acid, and solid oxide. So based on different electrolytes, different types of system, and also the operating methods, we have different types of fuel cell. So let's go through one by one. So the most popular one are proton, alkaline, and solid oxide. So in polymer electrolyte membrane fuel cell or PEM fuel cell, it exhibits at it exhibits high power density compared to other types. So the power density is very high as compared to other, constructed from a proton conducting polymer electrolyte membrane. So the membrane should be proton conducting. Membrane should be hydrated to maintain conductivity, cannot operate at temperature greater than 90 degrees centigrade. Limitation: membrane is coated on either side with platinum based catalyst and porous carbon electrode support material. So we are having porous carbon. Why porous? So that the hydrogen can disperse all over the anode. So membrane is coated on either side with platinum based catalyst and porous carbon electrode support material. Electrode catalyst membrane catalyst electrode structure is membrane electrode assembly, MEA. It's called MEA. And the low temperature operation of PEM fuel cell makes it suitable for portable application. So because it's operating at low temperature, because we cannot up 90 degree, we cannot go. So it's like 70 to 80 degrees centigrade. It's a low temperature. So it is suitable for portable application. The reactions: half cell reaction at anode, hydrogen oxidation. So 2H2, 4H plus 4 electron, and cathode O2 plus 4H plus 4 electron, 2H2O. This electron is coming through the external circuit and the hydrogen is coming through the electrolyte. So overall reaction is 2H2 plus O2, 2H2O plus electric energy plus heat. Now what is the difference between fuel cell and electrolyzer? Because now you have also heard the PEM electrolyzer. So what is the difference?
In the electrolyze, we produce the hydrogen. In fuel cell, we use the hydrogen. And in the electrolyze at the cathode electrode, we produce hydrogen. And whereas in the fuel cell at anode, we have to supply the hydrogen.
Okay, also a major difference also. Other difference? Anybody else? So what is the input in fuel cell and what is the input in the electrolyzer?
In electrolyzer, water is the input
Only water.
and electricity.
Yes. Water and electricity, because electricity is very important, na? It's very costly for the electrolyzer. So that is the issue actually. So electrolyzer, the input is water and
Uh, Water and electricity.
what are the outputs?
Outputs is H2
Mm-hmm.
and
Oxygen.
Yes. So basically you can see the reaction here itself, na? So this is the reaction for fuel cell, in which hydrogen is reacting with the oxygen and generating water and electricity.
yes.
So just opposite of this reaction, you will supply the water and electricity and you can get hydrogen and oxygen. Okay, so it's fuel cell, and reverse mode, it becomes the electrolyzer. So now alkaline fuel cell, it was used in Apollo mission by NASA. It can operate at wide range of temperature So it have high solubility, low cost KOH as electrolyte. Okay, so here you can see a difference between the PEM and alkaline. So here the electrolyte is in liquid form. In the PEM, the electrolyte is in solid form. So alkaline cell can use non-noble metal catalyst and have lesser crossover problem unlike PEM fuel cell. It produces current densities similar to PEM fuel cell when ambient air is used as oxidant. So the reaction involved here is anode is 2H2 plus 4OH minus 4H2O plus 4 electron. Cathode O2 plus 2H2O plus 4 electron 4OH minus. Now what is the difference between the alkaline fuel cell reactions and the PEM fuel cell reaction? What is the difference you can observe? So you can see these reaction and see these reactions. So if you compare the overall reaction, this one is same. The overall reaction is same, but the half cell reactions that are happening at anode and cathode, they are different. What is that difference actually?
Okay, in alkaline in the anode, hydrogen is reacting with the hydroxide, basically the alkali.
Mm-hmm.
But in PEM, the H2 is breaking in H plus and electron.
Okay.
And cathode. Cathode is
So if I consider the electrolyte, so what is the purpose of electrolyte in PEM fuel cell and what is the purpose of electrolyte in alkaline fuel cell? Just very common difference. Try to observe, because you know electrons are transferring from the external circuit. Only the ions are transferring from the electrolyte. So what is that difference in the PEM and the alkaline?
In the PEM, hydrogen ion transferred to the electrolyte, whereas in alkaline, hydroxide ion is transferred to the electrolyte.
Yes, this is the major difference. Yeah. So very important. So here you can see the H plus ion are that is exchanging between the anode and cathode. Okay, and full cell reaction is this. That is similar to the alkaline, but here thing is that the H plus ion is involved, and here the OH minus ion is involved. Okay, due to these only the reactions are different, the half cell reactions are different, but the overall reaction is same. So the ion is playing very important role. So in each fuel cell, this ion transfer is different. Okay. Now the phosphoric acid fuel, so it's a first commercial fuel cell for stationary application. Uses highly concentrated phosphoric acid as electrolyte. Need to have acid resistant components because we are using the sulfuric phosphoric acid. Tolerate to CO. Prudent choice of fuel. Sulfur need to be removed. Sulfur is limitation. Low efficiency, high weight. So anode reaction is 2H2, 4H plus 4 electron. Then cathode O2 plus 4H plus 4 electron 2H2O. What is the difference here? Here also the electrolyte, which ion the electrolyte is transporting?
Hydrogen
So
ions.
yes, here also between the anode and cathode, the electrolyte is transporting the H plus ions in phosphoric acid, similar to the PEM fuel cell. But here we are using the phosphoric acid as an electrolyte. Molten carbonate fuel cell, it is a high temperature fuel cell. Electrolyte made of molten carbonate salts require carbon dioxide at cathode. Here we require carbon dioxide at cathode. High temperature of operation created issue related to the mechanical stability. More resistance to impurities than other fuel cell because it's operating at high temperature, so it can resist to more impurities. Okay. The disadvantage is short life, high cost. So reaction is anode 2H2 plus 2CO3 2 minus 2H2O plus 2CO2 plus 4 electron, and cathode O2 plus 2CO2 plus 4 electron 2CO3 2 minus. So which ion? Carbonate ion is involved. Okay, overall reaction is similar. Now SOFC, solid oxide fuel cell. So due to high operating temperature, it has fuel flexibility. You can reform the fuel inside it. It uses solid electrolyte issues related to managing liquid are avoided. So in this also solid oxide, so electrolyte is solid as compared to other fuel cells. Those which are using the liquid electrolyte, so you can remove those limitations. So use of solid electrolyte reduces electrolyte thickness. So we can reduce the thickness of electrolyte, decrease the losses, produce high quality byproduct heat because working at very high temperature. So the grade of heat at high temperature is also good. That can be used for cogeneration. High temperature causes material issue, need to lower cost of ceramic structure. So reaction is 2H2 plus 2O, 2H2 plus 4 electron, and also here CO can be also used. CO plus 2O minus 2CO2 plus 4 electron, and cathode O2 plus 4 electron 2O minus. Overall reaction is this. So what is the difference here as compared to other fuel cell?
Oxygen ions are
Yes, so
transport.
oxide ions are involving. So here we can have a quick comparison. So PEM fuel cell, polymer electrolyte, alkaline, phosphoric acid, molten carbon, and solid oxide fuel cell. So if we compare the operating temperature range, so it can operate 40 to 80, then alkaline 65 to 220, phosphoric 205 degrees centigrade, and 650, and 600 to 1000. Then electrolyte. So here we have hydrated polymer ion exchange membrane. So Nafion is a material which is widely used. An alkaline mobilized or immobilized potassium hydroxide in asbestos matrix. Phosphoric immobilized liquid phosphoric acid in silica carbide matrix. And molten carbonate immobilized liquid molten carbonate in LiAlO2 and SOFC perovskites. Electrode are made of carbon, platinum, carbon, nickel and nickel oxide, peroxides and peroxides, metal cermate. Catalyst, up to phosphoric acid we use platinum as a catalyst. Here the electrode material itself is used as a catalyst. Charge carrier H plus, OH minus in alkaline, H plus again in phosphoric acid, carbonate ions MCFC, O2 minus in SOFC. So the fuel compatibility. Here hydrogen methanol, polymer electrolyte, hydrogen in alkaline, hydrogen phosphoric acid, hydrogen methane, and CO. Okay. Now the components of a PEM fuel cell. So in the PEM fuel cell, we have just read MEA, membrane electrode assembly. So this constitute polymer electrolyte membrane, catalyst layer, and gas diffusion layer. So this permits necessary ion to pass between the anode and cathode. Catalyst layer. On anode, the catalyst enables hydrogen molecules to be split into protons and electrons. On the cathode, the catalyst enables oxygen reduction by reacting with the protons generated by the anode, producing water. The gas diffusion layer facilitates transport of reactants into catalyst layer and removal of water formed. In the hardware, we have bipolar plates and gasket. The bipolar plates provide electrical conduction between cell and strength to the cell stack. The gasket is added to around the edges of MEA to make a gas tight seal. Leakage should not be there. Now the irreversibilities in fuel cell. So power produced by fuel cell stack is represented by the current density multiplied by geometric area multiplied by voltage from the fuel cell stack. So by this you can calculate the power. Voltage from a fuel cell stack, voltage from each fuel cell, and number of cell in the stack. Because each fuel cell we can only go the theoretical voltage 1.23. You can go up to 0.7, 0.8 like that, 0.9. It depends on the temperature, fuel concentration, and so many things. So normally you can get 0.8, 0.9. So if you want to have more voltage, you need to connect more cells. You need to have a stack. Just a minute. Okay, now output voltage of a fuel cell equals to reversible voltage of cell minus irreversible losses. The reversible voltage of a cell is the voltage under thermodynamic reversible condition, and irreversible loss is the over potential. Okay. So the type of over potential, there will be activation over potential, ohmic over potential, and concentration over potential. This is due to the activation is due to the slowness of reaction on electrode surface, ohmic resistance to the flow of ions and electrons, and the concentration mass transfer limitation at high current densities. Now the polarization curve are used to see the performance of a fuel cell. So it measures the performance. Real output voltage equals to idle voltage thermodynamically predicted minus activation ohmic plus concentration losses. So here you can see the idle voltage. Okay, and this is the actual voltage. So it's cell potential, then the activation loss initial phase, then the ohmic loss, and then the mass transportation loss. So obtained by drawing out fixed current from a fuel cell and by measuring the corresponding voltage, cell voltage versus operating current density. So lower current density, so the losses directly depend on the current density. Ohmic losses dominate in normal operation. High current density gives high power density but result in lower efficiency. Because at higher current density, this mass transportation losses will increase and it reduce the voltage in a dramatic manner. Temperature losses decline exponentially with increasing temperature. Higher the activation energy, higher the impact of temperature. Impact of temperature on cell resistance varies with material. For aqueous electrolyte, high temperature leads to membrane dehydration and loss of conductivity, and the mass transport loss is not affected by temperature. So it's also playing a very important role. Now the pressure increasing in the operating pressure has benefits. So if you increase the pressure, then the gas solubility and mass transfer rates increases with pressure. Electrolyte loss by evaporation reduced at high pressure. Also a disadvantage. You need to thicker the piping, expense of pressurization. Now the gas composition. So electrochemical reactions cause gas composition changes at inlet and outlet of fuel cell. Changes in the gas composition cause reduction in cell voltage, and cell voltage adjusted to lowest electrode potential given by the Nernst equation. Now the recent developments in fuel cell. So fuel cell will help in realizing the global goal of green energy transition. Okay, because we can directly use the hydrogen and the output is the water. So there is no emissions. Zero emission is the most attractive aspect of fuel cell in the market. The key player in the market includes Ballard Power System, Fuel Cell Energy Incorporation, Mitsubishi, Plug Power, and Cummins. Fuel cells are widely explored for distributed power and vehicular application. PEM fuel cells have wide scope in automobiles due to longer driving ranges and lesser refueling time when compared to the electric vehicles. Asia Pacific is one of the promising regional market for fuel cell on account of favorable government policies in China, Japan, South Korea, as well as due to rising interest in heavy duty transport and energy storage. So in 2020, South Korea surpassed the US and China and gained the leading market share in FCEVs, fuel cell electric vehicles, more than 10,000 vehicles. In March 2021, Toyota Corporation unveiled a new hydrogen production facility and refueling station at its decommissioned car factory in Melbourne, Australia, ahead of the arrival of its second generation fuel cell car, Mirai FCV. In December 2021, Hyzon Motors announced the delivery of 29 fuel cell electric trucks to be used by major steel conglomerate in China. In December 2021, Edison's Motors signed an agreement with Plug Power to develop and market a hydrogen fuel cell powered electricity bus. And as per the IEA Global Outlook 2021, China accounts 94% of global fuel cell buses and 99% of fuel cell trucks. So you can see the fuel cell is developing at very faster rate. The fuel cells are electrochemical devices convert chemical into electrical energy. We have covered this: efficient, reliable, scalable, no pollutants, released and silent operation, different types of fuel cell and can be used based on the application requirement. The cost is a major challenge, but economy of scale will come down because the cost is high because the production is very low. If we go through the mass production, then automatically the cost will come down. The ideal efficiency of fuel cell is given by which of the following expression: A, useful energy upon delta H, B, delta G multiplied by delta H, 0.83 V actual upon V ideal, and delta G by delta H.
Delta G by delta H.
Okay, we have an answer. Anybody?
C. It's C 0.83 V actual by V ideal.
Okay, we have two answers. What is the delta H and delta G?
Gives energy and enthalpy.
Sorry,
Gives energy delta G
and enthalpy.
enthalpy.
The correct answer is delta G by delta H. It's ideal efficiency. If you go through some previous slides, yeah. So the ideal efficiency is the delta G by delta S. This 0.3 V actual upon V add is thermal efficiency. The flame speed of a hydrogen fuel engine is space compared to the flame speed of a hydrocarbon fuel engine. High, low, equal depends on fuel concentration and ignition source.
It is high.
High.
Okay. And what is the value of that? How much high?
10 times.
13 times.
It almost 10 times higher. The flame speed of hydrogen fuel engine is high compared to the flame speed of hydrocarbon fuel engine. Which is the commonly used fuel in spark ignition engine? Diesel, hydrogen, petrol, biodiesel.
Petrol, hydrogen.
Petrol.
So we know the petrol is widely used fuel in the spark ignition engine. Okay. The consumption of fuel in SI engine is function of pressure, function of flame speed, and the function of both flame speed and pressure, neither a function of pressure and flame speed.
In function of both flame speed and pressure.
D.
C.
No, neither a function of pressure and the frames.
Sorry.
Function of pressure is confirmed, but confusion between A and C.
So function of pressure is confirmed.
It is depends upon the load.
Then,
The load.
then B. Function of flame speed.
Okay. Anybody?
Sir, neither the function of
Is slopes
pressure
line,
and
neither one.
neither one.
Okay.
Because the engine consumption depends based on load, engine load.
No, consumption of fuel in SI engine. Okay. So now let's discuss this question because we have multiple opinion on this question. Okay. Now let's start from the base. What do you mean by the consumption of fuel in SI engine? First thing first. What do you mean by the consumption of fuel in SI engine?
Burning of fuel within the piston. Maybe
Burning of fuel per cycle. Burning
Okay.
of fuel per cycle. What is the consumption?
So you can consider, okay, the burning of fuel per cycle, or you can say, yeah, you can say per cycle, or as we increase the power output, the consumption will increase or lower.
Increase.
Power output is increasing. Fuel consumption also higher.
more cycle, more power.
More? No, more cycle, you mean to say RPM?
Yes.
No, the engine size will increase if the power is increased. Cylinder size.
No, just tell me one thing. If is RPM is related to the consumption? Suppose your engine is having like say 1500 RPM.
Yes.
Yes,
And now-
actually the equation is the torque into RPM is the power. So if you keep torque same, so if RPM increase, then power definitely will increase.
So if you are having 1500 RPM and then 3000 RPM, so which option A or B will consume more fuel?
B.
3000.
Yeah, why? Because basically the it will have more inlet strokes, na? Because in 1 minute you are having 3000 RPM as compared to 1500 RPM. One of you is unmuted. Please mute yourself whenever, because we are having background noise. Okay, whenever you want to say something, then only unmute yourself. Okay. So we are having two scenarios, option A and B. So A, we are having 1500 RPM and then 3000 RPM. So basically we are increasing the RPM. So it means that in particular time frame, there will be more inlet strokes, or more times the fuel inlet will be there. Okay, the power stroke, more power stroke will be there. Okay, so more power stroke means that power output will be, more power output will be there. Okay, the consumption will increase. Okay, now the question is, the consumption of fuel in SI engine is function of pressure. And now let me know one thing, in your SI engine, what is the configuration? You are having inlet, then exhaust, there's your piston, and then there is a spark. So let me know one thing, do we pressurize our air fuel mixture before inserting into the piston cylinder? Hmm? Anybody?
Supercharging engine, we are pressurizing the air
No,
flow.
yeah, supercharging don't go in that aspect. Actually, I'm just asking a basic simple. Supercharging, yeah, we are doing, but still my question does, first we are I think in SI engine. So supercharging normally we do in the CI engine, na? In
No,
SI engine,
here we are not compressing before the injection, because we are basically engine cylinder is sucking the air fuel mixture. Okay,
yes,
so
yes.
then the inlet port is get closed, and then the compression happen.
So what do you think? My question is we are inserting the air fuel mixture at a high pressure or not?
No.
Atmosphere pressure only air fuel mixture enters.
Sorry?
In the atmosphere pressure, below the atmosphere pressure, air fuel enters into
Yes,
the cylinder.
yes. So what is the option, function of pressure? So definitely it is not a function of pressure, because we know that if you are having a engine from a maker and that is working at a fix, that is having, like if SI engine, that for that engine, when we practically use a particular engine, we don't tweak the parameters, we don't tweak the compression ratio, we don't tweak anything else, we just only put the petrol and just produce the power. Okay, now only think in that way. So in that way, the pressure is not playing important part, because it's only we are giving the fuel at less than atmosphere, like from the carburetor, less than atmospheric pressure is sucking the fuel. Okay, and also the compression ratio is fixed. So in the compression stroke, it will automatically compress. Okay, it is already fixed, we are not changing it. So how the consumption is connected to the pressure? So no, it is not connected with the pressure, because pressure is already fixed. Okay, it's not changing. So what will change if you increase the RPM? Is the pressure is changing? No. In each stroke, in each compression stroke, the compression ratio is fixed, so the pressure is already fixed. If you're increasing the RPM, the thing is that in 1 minute there are more double of compression stroke are there, more overall strokes are there. Okay, so you can eliminate the option A. Now the function of flame speed. Now what does this flame speed mean?
Propagation of flame from the spark point.
Yes,
How quickly it will burn the mixture inside the cylinder.
yes, right, very good. So suppose this is my cylinder, okay, and this is the topmost corner, and this is the TDC, your TDC. Okay, and here is your spark plug. Now when your air fuel mixture is here. Okay. Now, when you, because we know that piston will only go up to this point, TDC point, and at this point, your both inlet and outlet ports will be closed. Once it reach here and again coming down, then what will happen? Your exhaust port will open. Or what? Or your inlet port will open. What happens?
Low pressure.
Exhaust port open after
Exhaust.
combustion.
Exhaust and make the low pressure.
Yes. So the exhaust port will open because it is already pressurized. So this section will start. So this burned the commercial products will go out. Okay, because it's a high pressure, outside low pressure, so it will go out. So the thing is that yeah, yeah,
After spark, the expansion will happen. What it will do, that time the port will not be open. So, due to the energy inside this portion, so our cylinder head will go down, so that the crank will rotate. So after that, when the burn that complete, there after that only the port will open, because that cylinder will again go to the TDC. So when it will reach to the TDC, it will push out the flue gas out. Okay. Again, it will okay. So after pushing out that the port will close, and it will again suck air fuel mixture, and the inlet port will open.
okay. So just I think I'm confused a little bit. So you mean to say in the power stroke, both port will be closed, right?
Yes, yes.
Yes, yeah. So at that time, the energy will be stored in the, I think, the flywheel, and the next port will and that time. So the first is the suction stroke, then the compression stroke, right?
Yes.
Yes. Then expansion.
Yeah. Then the, you can say,
Expansion.
the expansion or power stroke,
Yes.
and then the
Then actually
exhaust.
exhaust.
The exhaust, right, right. So first the piston will come down, then it will compress, then the expansion will be there, and then the exhaust will be there. So yeah, both port will be closed. So yeah, thanks for the correction. So yeah, the question now, the point is that in this point, the flame speed will come into picture. Okay, so in this complete stroke, okay, the expansion stroke, okay, it will happen in certain duration. It reached here and it will go down. So if you are having very low RPM, then what will happen? So maybe your spark is sufficient to ignite up to this, and then already the stroke is started, and maybe the last front was not ignited at particular time. Okay, and your expansion stroke is already, your piston is coming down, and maybe the temperature is not sufficient, or any reason, maybe the whole fuel is not burnt. So what will happen? You will have less power. Okay, and also you will have uh, in the combustion also, the improper combustion will be there. So you can say, what do you say, the emissions will be more. Okay, now if you increase the RPM, if you increase the RPM, then these strokes are happening very fast actually. So overall the timing will change. So that improves. And also the flame speed, if you compare the flame speed, so for the hydrogen, the flame speed is very fast actually, 10 times faster. So that will quickly combust the whole fuel. That's the reason we discussed So basically the consumption of fuel in SI engine is a function of flame speed. So if you increase the RPM, then you have more power, the consumption will be more. Okay. So the pressure is not the so the consumption is not connected to the pressure, it is connected with the flame speed. Then the option C is also incorrect because pressure is not there, neither a function of pressure and the flame speed no. So the answer is B, function of flame speed. Okay. Okay, let's move further. Okay, only 5 minutes left. Okay, just quickly go through the next questions. The gaseous hydrogen occupies space in engine compared to the gasoline vapor in engine. Less, more, equal depends on the design of engine. Quickly, you know the density.
It's a more volumetric
Yes.
density.
Yeah, so we know that it required more space. In which fuel-based engine the knocking is higher? Hydrogen, petrol, diesel, dual fuel.
Hydrogen.
Hydrogen.
Yeah, because the flame speed is very high. The last portion of the fuel front will be burned before its time, so that can create a sound, that's knocking. So in the hydrogen-based engine, it will be high. The membrane most commonly used in PEM fuel cell is Nafion, polyamide, cellulose, peroxide.
Peroxide.
No, peroxide is
It,
used in the solid oxide fuel
it
cells.
is polyamide. Polyamide.
No,
Nafion.
Nafion, yeah. So
Okay, okay.
Nafion is a very popular name. So Nafion is widely used in the PEM fuel cell. The electrolyte used in the phosphoric acid fuel cell is H3PO3, KOH, H3PO4, H2SO4. So phosphoric acid, we use the phosphoric acid.
H3PO4.
Yes, correct. H3PO4. In thermal sensor, which parameter is used to measure or detect hydrogen? Thermal conductivity, thermal diffusivity, refractive index, capacitance.
Thermal
Re,
conductivity.
no, refractive index. Thermal sensor. Okay.
Yeah,
So
thermal
it is thermal
sensor.
conductivity. Thermal
Yes,
conductivity.
thermal conductivity.
Conductivity.
Which sensor shows the logarithmic variation in sensing hydrogen concentration? Potentiometric, amperometric, thermal sensor, work function based sensor. So if you go through the electrochemical sensor and see the Nernst equation section, so the potentiometric sensor shows the logarithmic variation because the term is in the ln. What is the working principle of acoustic sensor? Change in optical properties of piezoelectric material, change in surface properties of piezoelectric, and change in surface and optical property of dielectric material.
Change in surface property of piezoelectric material.
Yes, right. So we use the piezoelectric material and use surface properties change to measure the hydrogen concentration in acoustic sensors. So hydrogen is also used as an additive. So we can use the hythane, 20% H2 and 80% methane. Okay, or in a natural gas. So it can give you high flame speed of H2 mixed with low flame speed of methane. Gives better performance than methane alone. Emissions are reduced. No engine modification required at this mixture ratio. And existing fuel supply chain can be used. And we can also mix hydrogen with diesel. So small fraction of hydrogen, 5 to 7%, improves engine efficiency and reduce emissions slightly, significantly. H2 is supplied pre-mixed with air in existing diesel engine with little modification. So during the compression itself, we are supplying the H2. High burn rate of H2 ensure better and complete combustion of fuel. Then there is significant reduction in emissions, but NOx emission is high. Okay, so thank you everyone. This is from my side for today's class. So any doubt? So if you have any further query, so you can email me. I will try to respond as soon as possible. Thank you. Thank you for joining.
Okay. Thank you. Thank you.
Thank
Thank
you.
you.
Thank
Thank
you.
you.
Thank you.
Thank you.